Could black holes be the key to a quantum theory of gravity, a deeper theory of how reality, of how space and time works? Well, I think so. It's interesting. These objects, which have been known, I would say, for 40 or 50 years, but theoretically for the best part of a century, have always been fascinating.
Black holes are one of the most incredible phenomena humanity has ever known. They aren't objects, but extreme indentations in the fabric of space-time, places where physics, time, and light itself lose all direction. In these dark regions, the universe begins to operate by rules so strange they defy belief. Light is bent, time nearly stands still, and energy can seemingly emerge from nothing. It sounds like science fiction, but all of it has been confirmed by mathematics and by the very images we have managed to capture. So, are black holes the ultimate limit of our reality? Or are they a doorway to a world we have yet to comprehend? In the universe, nothing lasts forever, not even the stars that seem eternal. Every star has its own life. It is born, it shines, and then it ends. And that very end, if it's violent enough, can give birth to what we call a black hole. A massive star, dozens of times larger than our sun, is like a colossal engine. In its core, atoms constantly collide and fuse, a process that generates energy, pushing the outer layers outward and preventing the star from being crushed by its own gravity. But the fuel doesn't last forever. When the star burns through its hydrogen, its primary fuel source, it begins to fuse heavier elements: helium, carbon, oxygen. This is the final stage. As the core grows heavier and the energy produced is no longer enough to fight against gravity, at a certain point, the balance is broken. The core collapses almost instantly, causing the outer layers to rebound and explode. This is a supernova, an event that can outshine an entire galaxy for weeks. Most of the stars blasted away, leaving only the dense core behind. If that core is light enough, it becomes a neutron star, a tiny sphere with the mass of millions of Earths. But if it is massive enough, nothing can stop the collapse. Matter is compressed until it has no form, and a black hole is born. Humanity first learned of black holes in the 1960s. Astronomers detected an unusually strong X-ray source in the constellation Cygnus. They named it Cygnus X1. The strange thing was, there was no visible star there, yet something with the mass of 15 suns was present. After years of analysis, only one logical explanation remained. It was the first black hole to be discovered indirectly. From that moment on, the concept of a black hole was no longer just a theory. It was a reality, a part of our universe we can only observe by its effects on its surroundings. And as scientists delved deeper, they realized something even stranger than the black hole itself. What makes it so terrifying isn't just that it swallows everything, but how it distorts time and space around it. When a star collapses into a black hole, it's not just matter that gets crushed, space and time around it are warped as well. The gravitational pull is so strong that everything is stretched. If you were to get close, your watch would tick significantly slower than a clock far away. And if you took one step further, time quite literally would stop. This boundary between being able to return and being trapped forever is called the event horizon. Once you cross it, nothing, not even light, can escape. To a distant observer, an object falling in would appear to slow down, dim, and then vanish. But for the object itself, everything would feel normal. It would simply continue onward, until all definitions of time or direction become meaningless. It's a simple concept to state, but it pushes the limits of human understanding. Einstein once said, "Matter tells space-time how to curve, and space-time tells matter how to move." In the case of a black hole, this relationship is so extreme that time itself is bent. Near the event horizon, time and space essentially swap roles. You can only move inward, never out, as if inside has become your inevitable future. We cannot see inside a black hole, but we can see what happens just outside of it. Light and matter being pulled in form an accretion disk, a brilliant, swirling vortex of superheated gas rotating around the black hole. The temperature there reaches millions of degrees, emitting X-rays so powerful that our orbital telescopes can detect them from billions of light years away. What we call an image of a black hole is not a picture of the object itself, but of the shadow cast by its event horizon, the point where light is bent around a region of absolute darkness. In 2019, when the Event Horizon Telescope team released the first ever image of the black hole M87 Caus, many thought they were seeing a dark spot in a ring of fire. In reality, it was the light that was forced to travel around it, warped by the universe in a way that can happen nowhere else. A black hole doesn't just consume matter, it changes how time itself works. And this leads to a paradox if everything is trapped inside forever. Where does all that energy and information go? This seemingly small question is what Stephen Hawking dedicated his life to answering. For years, it was believed that a black hole was a perfect prison. It swallowed everything and never gave anything back. But Stephen Hawking proved the opposite. Black holes can, in fact, glow. This sounds impossible. How can something with a gravitational pull so strong that even light cannot escape possibly glow? The answer lies in the world of quantum mechanics, where empty space isn't empty at all. According to quantum theory, the vacuum of space is constantly fizzing with pairs of virtual particles, a particle and an antiparticle, that pop into existence and then annihilate each other in an instant. Normally, this happens so fast it has no effect. But if it happens right at the edge of a black hole's event horizon, the situation changes. One of the particles might fall in, while the other escapes before they can recombine. The result from an outsider's perspective: it looks as though the black hole is emitting particles. And to pay the cosmic price for this, its mass must decrease ever so slightly. This phenomenon is called Hawking radiation. It is incredibly faint, far too weak to be measured with today's technology. But theoretically, it reveals something unprecedented. Even a black hole can slowly lose energy and, eventually, disappear. The process is unimaginably slow. A black hole with the mass of our sun would take around 1066 years to completely evaporate, a timescale billions upon billions of times longer than the current age of the universe. But in principle, it happens. This means that black holes are not immortal. They live, they glow faintly, and then they die, just on a timescale we will never live to witness. This discovery stunned the world of physics. It was previously thought that information falling into a black hole was lost forever, a violation of the fundamental laws of physics. But if a black hole emits radiation, then energy and perhaps information is not completely lost. Hawking had turned the black hole, a symbol of absolute permanence, into a dynamic system that changes over time. And most importantly, he showed that even in the darkest place in the cosmos, there is a way for energy to escape. But if black holes can release energy, could humanity ever find a way to harness it? It sounds like pure science fiction. But the idea is not as far-fetched as it seems. Some black holes don't just sit still in space, they spin. And they do so at incredible speeds. When a massive object rotates, it doesn't just move itself, it drags the very fabric of space-time around with it, like twisting a spoon in honey. This phenomenon is known as frame dragging. Physicist Roger Penrose proposed a daring idea based on this. He imagined that if we were to drop an object into the swirling region of spacetime around a rotating black hole called the ergosphere and split it in two, allowing one piece to fall in while the other escapes, the escaping piece could emerge with more energy than the original object had. This profit comes directly from the black hole's rotational energy. In other words, we would have extracted energy directly from spacetime itself. Theoretically, the efficiency of this process could be as high as 20% of the object's rest mass. That number might sound small, but for comparison, the nuclear fusion that powers our sun converts only about 0.7% of mass into energy. This means that if humanity could ever master this principle, a rotating black hole would be the most efficient energy source in the entire universe. Of course, we can't do this in practice yet. No one can throw matter at a black hole and measure the energy that bounces back. But in nature, a similar process may have been happening all along. As matter is pulled toward a black hole, it doesn't fall straight in but spirals around, forming the superheated accretion disk that emits powerful X-rays. At the same time, from the black hole's poles, relativistic jets, colossal beams of plasma are launched outward, stretching for millions, or even billions, of light years. The paradox is this: the very thing we call an inescapable pit is responsible for creating the most powerful energy beams in the universe. This doesn't mean light is escaping from within, but that the space around the black hole is being stretched and energized. In that fringe region, everything matter, energy, and even time blends into a single, unified system. If there is one place in the universe where Einstein, Penrose, and Hawking are all correct at the same time, it is right at the edge of a black hole, the place where the laws of physics are pushed to their absolute limit. As astronomers observed black holes more closely, they realized that not all are created equal. Besides the smaller ones formed from exploding stars, the universe is home to a class of giants so massive they are almost impossible to imagine: supermassive black holes. They reside at the center of most galaxies, including our own Milky Way. The mass of these titans can range from millions to billions of times that of our Sun. And surprisingly, despite their immense size, most of them are very quiet. At the heart of the Milky Way lies Sagittarius A, a black hole weighing about 4.3 million solar masses, located 26,000 light-years from Earth. Most of the time, it is largely dormant, occasionally swallowing a stray cloud of gas or dust, letting out a few faint flares, and then falling silent again. But not all black holes are this well-behaved. When a supermassive black hole begins to feed at a high rate, the accretion disk around it can shine brighter than thousands of galaxies combined. When this happens, it becomes a quasar, one of the great beacons of the cosmos. A prime example is TON 618, a black hole with a mass of about 66 billion suns. It is so far away, 10.8 billion light-years, that the light we see today is an image of it when the universe was just a fraction of its current age. Just think, before humanity existed, before Earth was more than just dust in a young star's disk, that monster was already there, devouring stars and blasting light across the cosmos. What puzzles scientists is how they grew so big, so fast, according to theory. It should take tens of billions of years to reach a mass of billions of suns. Yet many giant black holes already existed just a few 100 million years after the Big Bang. How did they develop so quickly? There are two main hypotheses. First, they were born from enormous seeds, primordial stars thousands of times the mass of the Sun that collapsed almost instantly. Second, they grew rapidly thanks to the environment of the early universe, where matter was so dense that food was never in short supply. Either way, these black holes don't just sit at the center of their galaxies, they shape them. Every time they feed, the immense energy erupting from their jets can sweep through the galaxy, clearing out gas and slowing down star formation. Because of this, a black hole and its host galaxy are intrinsically linked. As one grows, the other changes with it. In other words, a black hole isn't just a product of its galaxy, it's also the conductor that orchestrates how that galaxy evolves. Today, with telescopes like the JWST and the Event Horizon Telescope, we are seeing these cosmic giants at the edge of the observable universe for the first time, dark hearts residing in the earliest dawn of time. Each new discovery forces us to reconsider what we thought was certain. Looking at these giants, we see a familiar cosmic paradox. The thing that seems to destroy is actually the anchor that holds everything together. And perhaps, without them, galaxies and Earth itself could never have existed as we know them today. Black holes are proof of the universe's greatest paradox. The very thing that appears to be an agent of destruction is actually a key to understanding everything else. From these infinite voids, we have learned that the universe does not always operate as we expect. Space can bend, time can stop, and things we once considered certain turn out to be merely temporary. What makes black holes so special isn't that they consume everything, but that they force us to look beyond our own limits. Every time a theory is broken, we get one step closer to the truth. Perhaps humanity will never see what lies inside a black hole, but maybe the goal isn't to see, but to dare to ask the questions. And as long as we keep asking, as long as we remain curious, then even the darkness is no longer something to fear. If you want to continue exploring the paradoxes of the universe, where light and darkness tell the same story, be sure to like and subscribe for more.